Okay, let's go ahead and get some practice calculating some de Broglie wavelengths. Now, something we know that is the de Broglie wavelength is going to be related to the momentum. As such, the wavelength is Planck's constant divided by the momentum. And so if we have this electron, it's going to 6.626 times 10 to the minus 34. It's going to have some speed, and this is going to be the mass times the speed. So mass of an electron is 9.11 times 10 to the minus 31 multiplied by its speed, 4.7 times 10 to the 6. We're going to get a wavelength of 0.155 nanometers. And for the proton, we know that the mass of the proton is 1.67 times 10 to the minus 27th. And so this guy is going to work itself out to be 8.46 times 10 to the minus 14th meters. And what this kind of says is we know that the proton is about 1,000 times more massive than the electron, and so the wavelength has to be that much shorter. So as we get to larger and larger particles, we're talking smaller and smaller and smaller wavelengths, and we're far less likely to be able to observe this type of phenomenon. Now we'll have a hypothetical atom, and suppose we've measured some wavelengths from these various transitions, and we also observe that it takes 17.5 volts or electron volts to ionize this atom. That's going to tell us that the energy associated with that is going to be negative 17.5 eV, and we're asked to figure out what all of these energies are. Now, something that we know is we know that delta E is going to be equal to hc divided by lambda. And so let's take a look at the 1 to 5, or I should say the 5 to 1 transition. We know the wavelength associated with that, and so we can say delta E is going to be equal to h, which I'm going to use the h in electron volts, 4.136 times 10 to the minus 15th multiplied by c, 3 times 10 to the 8th. Divide that guy by the wavelength of the 5 to 1 transition, so 73.86 times 10 to the minus 9th, and I'm going to get my delta E to be equal to 16.79 electron volts. And so what that does is that tells me that the difference between negative 17.5 and that is going to be the energy of my n equal to 5 state. And so that tells me that this guy right here is going to be negative 0.71 eV. And now you're just going to do this again and again and again and again. And so you're going to do the 4 to 1, and you're going to figure out this is negative 1.1 eV. And you're going to do the 3 to 1 transition, and you're going to say negative 1.95 eV. And then you're going to do the 2 to 1 transition, figure out that's equal to negative 4.38 eV. Now for part B, what we're going to do is we're going to say, okay, well, delta E, now we're looking at the 4 to 2 transition. That's going to be equal to negative 1.1 eV minus negative 4.38 eV, and that's going to be equal to 3.28 eV. And so we're going to say lambda is simply going to be equal to hc over delta E. And again, I'm going to use the E or h in electron volts, so 4.136 times 10 to the minus 15th times 3 times 10 to the 8th divided by 3.28, and I'm going to get 378 nanometers. Now that does pass my field right test because this is still in the ultraviolet, but closer to visible light than any of these, and these have a lot of energy. This has less energy than those, so I get a warm fuzzy feeling about that. And last but not least, let's get some practice using determining the peak frequency of the Planck distribution. We're going to use Wien's displacement law, which is going to predict the maximum wavelength. And again, it's going to be 2.9 times 10 to the minus 3 divided by the temperature. And so for part A, the temperature is going to be 3 Kelvin. So it's going to be 2.9 times 10 to the minus 3 divided by 3, and we're going to get 0.966 nanometers, or I'm sorry, millimeters. And what we can then do is we can say, well, we know that the frequency is going to be equal to the speed of light divided by the wavelength, and so the frequency is going to be equal to 3.1 times 10 to the 11th hertz. Now for part B, we've increased the temperature, and actually we've increased the temperature by a factor of 100, and so that's going to decrease this by a factor of 100, and that's going to increase this by a factor of 100. So 3.1 times 10 to the 13th hertz. And for part C, you can make the same argument and say that it should be 3.1 times 10 to the 14th hertz.